So you're sure it's a cable and not the box?
No, it's a cable. I changed the. Yeah.
If you move the box there, does it do anything? Because, forget it.
Okay. All right, everybody, welcome to our private seminar. We invite the Ziyu Chen from University of Massachusetts on guest. Right. So let's welcome our speaker.
Thank you, Pei, for the invitation and the introduction. So it's a great pleasure to be here, and it's my first time to visit Yale. And today I will be talking about something about generative modeling, but it's more focused on the mathematical part. So I just heard some speaker just gave a talk about the generative modeling last week. So I suppose this talk will not substitute in this sense. Okay. So the outline of the talk today can be split in two parts. So in the first part, I will talk about when we have the knowledge of the underlying structure of the target distribution. So how can we utilize the knowledge to achieve the efficient generative modeling? And the second part of the talk is about, suppose we do not have any knowledge about the underlying distribution, can we develop some robust algorithms to achieve efficient generative modeling that is agnostic to the structure of the data distribution? Okay, so let me give you a rough picture of what generative modeling is. So you know well about the ChatGPT or image generations. And the overall picture of generative modeling is that suppose you have a bunch of training data that drawn from some unknown data distribution. And the goal is to simulate or generate a distribution that is parameterized, typically parameterized a family of neural nets that is as close to the unknown data distribution as possible. So in general, the goal of generative modeling is to try to find the optimal parameter theta such that the generated distribution is very close to the target data distribution. Okay. So here is the target data distribution. Here is the family of the distribution generated by your models. Okay, so in order to be able to capture or measure the discrepancy between the target data distribution and your generated data distribution, you need to come up with some notion of a distance, or formally is a probability divergences that can compare the difference between two probability measures. Okay, to better understand the notion of divergence, let me introduce one of the well-known generative models, which is the generative adversarial networks, or abbreviated as GANs. So in the GAN framework, okay, you have a set of real image data drawn from some distribution, and you want to learn a generator, typically a neural net, that can map some easy to sample distribution, such as like uniform distribution or Gaussian distribution, to the space of probability measures. So this is the generated distribution where you generate a bunch of fake images. Okay, so at the same time, you also want to train another neural network, which is called a discriminator, that tries to distinguish the real images and the fake images as hard as possible. So here is a problem formulation of the discriminator part. So you want to take maximization over all the discriminator function class such that the discrepancy between the generated distribution and the target distribution can be best distinguished. Okay, so this is the one formulation of the probability divergences where you take a supremum over some function class that tries to distinguish these two different distributions. For example, this H can be taken in the form like mean embedding, formalized here, and you take a supremum of gamma within, say, like some unit ball of RKHS or Lipschitz function class. Okay, so this is about the discriminator part. If you want to formalize the mathematical problem or objective of this GAN framework, so what you really want to get is the minimization of the probability divergence of the discriminator part. So you want to find the best generator that this discriminator can hardly distinguish between the generic distribution and target distribution. So the overall problem is really a mini-max problem. So the maximum part, it gives you the formulation of probability divergences. And you want to find the best generator such that this divergence between fake data and real data can be minimized. Okay, so one central question of generative modeling, or even more generally the machine learning, is typically machine learning with generic black box model requires big data to train. And suppose there are some structure of the data and we know the underlying structure of the data distribution. For example, you can consider conservation laws or some topological constraints and even group symmetry. So one potential solution is that can we leverage the underlying structural information to improve data efficiency, such in the sense that we can still achieve efficient learning with reasonable result even with limited data. Suppose we consider the underlying inductive bias of this symmetry or structure. Okay, so for the structures we will mention today, we will include group symmetry or heavy tails and low dimensional manifolds or even fractals. And for the first part of the talk, I will consider in particular group symmetry. So symmetry is ubiquitous. For example, in the medical image data, you can view the diagnosis result of the rotated copies should be the same. And in this sense, all the images should be invariant in the probability density with its rotated copies. And also on the other hand, for molecule generations, there should also be some symmetries. So your molecule generation should obey some symmetry rules to generate. Such that here you have a rotation symmetry, here we have some symmetries in the like physical laws over here. Okay, so formally, given a domain omega, we can define a group action on this domain such that this induces an automorphism from omega to itself. And for simplicity, we just consider the group consists of all the linear isometry such that each group element induces a map where is a matrix vector product such that the matrix is a unitary matrix. So this includes rotations and reflections, for example. Okay, so given the notion of group symmetry, we can define, we can provide a notion of G invariance. So we say a function is G invariant if the function composed with any group action is a function itself. And given arbitrary function class gamma, we denote this by this notation that it's subset of all the functions within gamma that are also G invariant. Similarly, we can define notion of G invariance for probability measures. So we say a probability measure is G invariant if it's pushed forward by any group action is the probability measure itself. For example, you can view again, take the rotation of images example. All the images have the same probability density as its rotated copies, where G is the rotation, you can see of the rotation actions. Any questions so far? Okay, so a little bit more mass formulation over here. So consider arbitrary functions that is not necessarily G invariant. So we can introduce a symmetrization operator to take an average over all the group elements or group orbits so that for any non-G invariant function gamma, the output or average function is guaranteed to be G invariant. And also we can produce a symmetrization of probability measures. So for each probability measure row that is not necessarily G invariant, after the symmetrization, we can produce a G invariant copy of that. So in particular, if this probability measure row is like discrete measure or empirical measure of finite samples, so the symmetrization gives you the data augmentation of these finite samples. Right? Okay, so one motivation to consider group symmetry. So here is one experimental result where we come back to the example of GAN to learn the rotated MNIST data with only 1% of training data. So here is the GAN as result to generate MNIST distribution with no knowledge of symmetry. So it's just a vanilla GAN without any knowledge of the symmetry. So here is the GAN with the same training data, but with the symmetry incorporated in both the generator and the discriminator. So on the right-hand side, the quality of the generated imagery is better, maybe slightly better than the left-hand side. Okay. So mathematically, the first question we want to ask is, okay, many people do like data augmentations, but data augmentation do not produce IID samples, right? But why do they help in practice? So suppose you have a set of images like this, you may think, okay, they might be IID, but actually they are conditionally dependent on these images, right? So in fact, they are not IID. Okay, so because we talk about probability divergences that is used to measure the discrepancy between the generated distribution and target distributions, so which is also the loss function for most of the for all the generative models. Okay, so in this sense, we will consider the problem from the divergence point of view. So for example, we'll consider the Wasserstein-1 metric. So it's the simplest type of optimal transport loss. So, but here we write in its variational form. So the supremum of the text function is over the Lipschitz function class. So actually here L should be equal to one Lipschitz functions. And another class of divergences is the so-called MMD. So it's the kernel-based method. So where this test function space is the unit ball of some RKHS. So it depends on the choice of the kernel, right? Okay, so the generic property of the divergence is that, so the quantity divergence is between any pair of distributions is always non-negative and is equal to 0 if and only if P and Q are the same probability measure of distributions. Okay, so in practice, we only have access to finite samples that are drawn from P and Q, and in particular, you can view P as a generated distributions and Q as a target distributions, where you have M samples from P and M samples from Q. And suppose both P and Q are G invariant with respect to some group. So we want to ask, can we really benefit from doing data augmentation? Okay, so one thing to note is that even though P and Q are both G invariant, but their finite samples are not, right? And also recall data augmentation does not produce IID samples. Okay, so the first result in terms of the empirical estimations of divergence is for the Wasserstein-1 metric, where recall we have a variational form over here for the D1 Wasserstein-1 distance, and this test function space is the Lipschitz-1 functions. And in this sense, we propose an estimator based on M samples from P and N samples from Q, where the knowledge of symmetry is encoded into the test function space. So here, in the estimator, we take a supremum only over all the G invariant Lipschitz-1 functions. So it's a subset of this gamma, such that this formulation, so where we restrict the function space to even a smaller one, it has been shown to be equivalent to the formulation of the Wasserstein-1 distance between the data augmented version of PM and QN. So recall SG is the symmetrization of probability measures. So even though PM and QN are not G invariant, but after symmetrization, they are both G invariant. So this is the data augmentation of PM, and this is data augmentation of QN over all the group orbits. Okay, so we provide the result in terms of the divergence estimations. So here we have real divergence quantities between P and Q, and here is the divergence estimator based on M samples from P and N samples from Q. So this is a non-asymptotic result. So this is upper bounded by some quantity like this. So in the simplest case where we have finite group, so you have a gain that is a factor of the group size in front of n and group size times n. So you can view it as, so without any group actions is basically m and n, but now you have incorporated group symmetry. So you have additional, like effectively additional samples as group size times m and group size times n. So this tells us data augmentation has an equivalent effect as if we have IID augmented samples, even though they are not IID, right? But the convergence bound provides IID form of the convergence in terms of the number of samples. Okay, so just one simple numerical verification. So suppose in the d equals 1 case, we have a whole domain as the unit interval. And as we increase the group size, the quotient space will shrink, right? If we define the group action as the translation, is correct? Okay, so here is the plot of the empirical divergences where we put P equals Q and we run like 20 replicas over here and we increase the group size by a factor of 4 each time. And on the right-hand side, we plot the ratio between the consecutive pairs of these two curves. So by the theorem, we have the diameter should also shrink by a factor of 4. So on the right-hand side, you can see, so this verify our theorem where this concentrated around 4. So because each time we increase the group size by a factor of 4. Okay. Any questions so far? Yeah.
What if the group is not finite?
Not finite, yes, great question. I will come back in the next slide. Yes, good question.
Should the ratio converge to 4 as you increase number of samples?
Say it again.
Should the ratio converge to 4?
Ratio, yes, so because
As we increase numbers?
increase the number of samples, so because the ratio is like between these two group sizes, right? Because the whole domain is fixed, right? So each time, according to the bound, so the ratio only reflects the diameter of the quotient space, right? So no matter the number of samples, it's because it's a non-asymptotic result. Okay, let's come back to your question. So what if the group is infinite? Okay, so suppose the group is infinite and suppose the quotient space has some scaling on the covering numbers. So such that we can get improvement. So originally we have D and D on the rate. Right? Now the D can be improved to be the D star, where also we do not see the group size because now it's an infinite group. Instead, we have an additional volume of the quotient space and volume of quotient space over here. So if the group is infinite, we may get improvement on the rates, but the improvement is reflected on the scaling of the covering number of the quotient space. So one particular example is when the whole domain is a d-dimensional submanifold and G is a compact Lie group acting locally and smoothly on this whole domain, then this D star is equal to the D minus the dimension of the group. Okay, so next result I want to show is about the MMD. So it's a kernel-based method. Again, we have estimations, the MMD estimations, where we again take the supremum over all the G invariant functions on the unit ball of the RKHS. So it's equivalent to compare the data augmented version of PM and QN. So the gain is reflected on this capital A, where the capital A is connected to this little a, that little a captures the decay of the kernel beyond the diagonal. So for example, you have Gaussian kernels, then it's maximized along the diagonal. So if you go away from diagonal, it should be decay. So this little a intuitively is, you have fast decay, then little a should be small. So for example, if little a is very small, if you plug in, you have capital A is approximately square root of 1 over group size for finite group. And you multiply this 1 over square root of group size into these two terms, you have 1 over square root of group size times m and 1 over square root group size times n. So similarly, you have an effect of IID data augmented samples, right? But it really depends on the kernels. So for example, in this example, we fix the domain and we increase the group size. So if you fix a Gaussian kernel like here, but you increase the group size of the domain, then you can see the gain stopped when group size equals 4, because according to theorem, it really depends on the kernel decay of the kernel. So in order to see the further gain, when you increase the group size, you need to select a smaller Gaussian kernel bandwidth to see a further decay when you have more group actions on this domain.
Can I ask a question?
Yes.
Is the math and what you are showing us the same as if I wouldn't look at P of G times M, meaning I have G times the size of G times M samples?
Right, G times M sample, G and G times N samples.
On the left.
On the left, yes,
Yeah.
yes, yes,
Instead of taking SG, you will take P of the size of G times the M samples.
yes.
Would
So
I get the same thing? on the
right, exactly. So this term, is actually all the data augmented samples PM. So effectively here we have G group size times M samples from P.
So we will get the same thing.
Yeah, these are actually the same mathematically. Yeah, indeed the same. Yes, right. But they are not ID, right? Mhm. Okay. So many more questions on this MMD.
Yeah, usually for MMD,
Yeah.
it doesn't really work.
Right.
Because MMD has only one scale,
Right.
so it depends on the kernel. You
Yes.
have to do MMD with a combination of kernels.
Right. So there's a work of MMD again. So they took like supreme over a class of family of kernels, but it's still not
rescale the kernel.
Right.
You wait, depending on the scale, then you're guaranteed.
Exactly.
Poser and Lipschitz and all of those things.
Yes. Even you take a family of the kernels, it may not work that well. Yeah. Okay, some extensions. Okay, first we want to highlight that this is the first result to quantify the gain by doing data augmentations. And later, our result was extended to continuous isometric groups on closed Riemann manifolds for Wasserstein 1 without using the covering number. But the difference is our method also works for asymmetric divergences. So we will come back to these asymmetric divergences in the later part of the talk. Okay, another question we want to ask, what if the domain is unbounded? So these two are related, so all will be addressed in the later part of the talk. So we have provide one explanation about data augmentation. They are not an ID, but they do help. And another question is asked, so in particular generative models, is there a better way than simply doing data augmentation? Because data augmentation is really something you only manipulate on the training data. So another way is to incorporate the knowledge of symmetry into the models, for example, into the neural networks. So there are some equivariant models, for example, structure preserving GANs or structure preserving diffusion models. So they will provide abundant numerical implementations for the effectiveness of these generative models. So the point they all make is that they both ensure the generative distribution is always tree invariant when they have assumption that the target distribution is tree invariant. But they never explain why this is necessary, or is it really necessary to generate like tree invariant distribution. Okay, so for example, if you want to embed the symmetry into the GAN architecture, so you have a generator and you have a discriminator. So you need to build the generator as some equivariant or invariant neural network, and also the discriminator as an equivariant or invariant neural network, such that you can ensure this G is G invariant. So in this sense, the built-in symmetry is reflected in the network architecture of the generator and the discriminator. So here is one simulations where you want to learn a Gaussian mixture with only 100 training data. So the Gaussian mixture consists of 4 Gaussians with 4 centers. You can view this group as a C4 group. And the first row is you use a vanilla GAN with no knowledge of symmetry. And second row is you use a GAN incorporated with half the symmetry. Basically, you know that you can go from one center to the diagonal center. And the third row is you have a GAN with full knowledge of symmetry. So each group action is generated by the one that takes you from one center to the next one. So you have full knowledge of the C4 symmetry. So if you compare the first 3 rows, you can see as you're building more symmetries of the knowledge or distribution into the GAN architecture, you'll have better performance with the same amount of training data. And the fourth row is in the same as the first row in the sense that they both have a vanilla GAN with no knowledge of symmetry, but the fourth row uses the full data augmentation. So it's a vanilla GAN with 400 training data with full data augmentation. So if you compare the bottom row with the top row, you can see data augmentation does help, but it's not that helpful compared to building symmetry directly into the models compared to the third row. Okay, so we have a theory for this group invariant GANs. Basically, we measure the average of the versus the one distance between the data distribution Q, which is assumed to be G invariant. And here is the generated distribution from n unaugmented samples and m samples from the noise source distribution, such that it can be a Gaussian. So this is guaranteed to be G invariant. Okay, so in particular, this provides us a bound in terms of this delta 3, which is the one we saw from doing data augmentation. But this can be possible only if you build in the symmetry into both the discriminator and the generator, such that you can get improved statistical error from the target distribution. Okay, so I want to emphasize more on this comparison between data augmentation and building symmetry into the model in the context of diffusion models. So in diffusion models, you keep adding noise, and then in the denoising part, you utilize knowledge of the score to doing backwards to remove the noise in some sense. So the related question we want to ask is that, can we learn more efficiently if the target data distribution is G invariant? So if so, how to quantify the improvement? So the short answer is yes, and we will show the model equivariance is more essential than doing data augmentation. This is also the first quantitative comparison between these two approaches for the equivariant generative models. Okay, so in addition to the G invariance, we want to introduce the notion of G equivariance. So we say a vector field S is G equivariant if it respects the group actions in this sense. So in particular, if the probability measure is G invariant, then it's a score function. So its score is defined as the gradient of the log of the density. Can be shown to be G equivariant. So a related symmetrization operator can be introduced. So for any vector fields, you can introduce a symmetrization operator to produce its G equivariant part, a counterpart of this generic vector field S, such that even though S is not necessarily G equivariant, then after symmetrization, you get G equivariant vector field. So this is a similar notion of the symmetrization of functions and probability measures. Okay, so the goal of our SGM is to learn a data distribution that is G invariant, and the drift term or the score function is typically approximated by some neural networks, such that the generating or denoising process can be written as a PDE like this, where we consider the domain to be bounded for simplicity. And if you run the denoising process and stop at time t, then m of t, the solution to this equation, is the generated distribution. And the idea is to either perform data augmentation, or you want to make this S theta to be G equivariant, because we know if the target distribution is G invariant, then its score function should be G equivariant. So will it help if we make the score approximation also be G equivariant? So this will ensure the generated distribution is always G invariant, because you initially condition respect the symmetry. Okay. So how can we learn the score approximation? So typically it's by solving the score matching objectives. So for example, you have a so-called denoising score matching. Basically, it's the L2 norm between the neural net approximation with the real score function. So this is the conditional expectation expansion. Or if you expand this L2 norm and remove the term with that is independent of S theta, you get the implicit score matching objective function. So this optimal S theta is learned by minimizing either of these two objectives. And they have a relation that this DSM objective is equal to ISM objective plus some L2 norm of the underlying distribution of the score of underlying distribution that is independent of the S you want to optimize. Okay, so we want to provide the result of the errors or some uncertainty quantification bound for the equivariant SGMs. So basically, we want to measure the Wasserstein-1 distance between the generated distribution and the target distribution. So the error can be decomposed into four components. So the first one is the measurement of the non-equivariance of the length score function. So which means it matters if you use equivariant S theta or non-equivariant S theta. And E2 is the score matching error with symmetrized vector field. And E3 is the sample complexity bound we saw in the first part of the talk is about the effect by doing data augmentation. And E4 is something independent of the number of samples is because you have some early stopping and time horizon. So we'll mention it later of what this means. So in practice, we only have finite samples or n sample drawn from the target distribution pi. And if we want to do data augmentation, then we denote it as pi gn. So it's basically we symmetrize over all the n samples. And because these n discrete samples do not have well-defined score function, then we typically will diffuse it for epsilon time. So which is equivalent to we convolve it with the heat kernel for epsilon time. And similarly, we can diffuse the symmetrized or data augmented samples for epsilon time. So, and the score matching function, or how do we learn the score function, is basically by score matching with eta. So eta is the solution to the heat equation that with initial condition that is already diffused by epsilon time with the augmented samples over here. So the initial condition is you have n samples and you augment all the n samples and it diffuse for epsilon time to get well-defined score functions. And then you do the score matching from this initial condition up to some time t. Does it make sense? Okay. So in particular, this pi n is not tree invariant, but its symmetrization is tree invariant. Okay. So here is the first result for the equivariant SGMs using data augmentation. So our assumption is that for each empirical measure pi n drawn from this tree invariant target distribution pi, and suppose domain is d-dimensional torus, so this has a periodic boundary conditions. So, and we assume there always exists a score approximation as theta learned by the DSM objective with early stopping. Early stopping means you corresponds to this epsilon, you diffuse the finite sample by epsilon time, such that this score matching error is always bounded by some ENN. So the score matching is performed in terms of the measure of augmented samples, right? So this is the notion in the last slide where we augment data and then diffuse by epsilon time and then run for some time you choose. This is the diffusion, the solution to the heat equation of the augmented samples. And you always have an upper bound for the score approximation norm bounded by A. So this can be achieved, for example, you have some constraint of the neural network parameters. So this is straightforward. Okay, then with this assumption, we show that the average of the Wasserstein-1 distance between the generated distribution and the targeted distribution has the following generalization bound. So the first part is some early stopping error. And second part is some exponential decay from the solution of the heat equation to its stationary measure. So these two are independent of the score approximation and finite samples. And the third part is you have ENN prime, where ENN prime can be further decomposed as ENN. This is the denoising score matching error. And the second part is the finite sample error. It's proportional to this finite sample error within the first part. So in the case of discrete group, we have this D1 between the augmented finite samples with the true distribution can be benefited from the data symmetry by effect of the group size if the group is finite. Okay. So now we want to quantitatively compare the equivariant score approximation versus data augmentation. So this gain appeared here for this sample complexity bound comes from the score matching with this augmented data. Okay, so in the first case where we have data augmentation, but we use non-equivariant vector fields as theta. So this gain comes from the score matching with augmented data, but we have to pay the cost of data augmentation. And this can be expensive if the group is large or even infinite. And another question we want to ask is that, is there any gain if we use G-equivariant vector fields as theta? Okay, so we provide the notion of so-called deviation of equivariance of a vector field with respect to some G-invariant probability measure. Basically, it's the weighted L2 norm between a vector field S and its symmetrized vector field, such that if S is already G equivariant, then the DFE of S with any G invariant probability measure rho is always equal to 0. So if it's intuitively highly non-equivariant, then this value should be large because it should be far away from its symmetrized equivariant version of the vector fields. So this DFE actually measures the non-equivariance of the vector fields. Okay, so the answer to this is yes to the second question. So because we explain this theory, so for any G invariant probability measures and any vector field S, so the probability measure is G invariant, but the S vector field is generic, might not be G equivariant. Then we have the following arrow decomposition. So the DSM arrow of the score matching of S with respect to probability measure rho can be decomposed as DFE of S with respect to rho plus the DSM score matching arrow using its symmetrized vector fields to approximate the score of the same probability measures. Such that because we know this JD is always non-negative because it's weighted L2 norm expanded in conditional expectations. So we have this ENN, we call it ENN comes from here, the score matching with this symmetrized data. So ENN equals JD such that it has a lower bound of this by the DFE. Okay, so this means ENN can be lower bounded by a large number if S theta is highly non-equivariant, right? So this means if we use data augmentation but use non-equivariant vector fields, we have a gain on this term in green, but this ENN can be large if we use non-equivariant vector fields or non-equivariant score approximation. Okay, another case is we switch the role between these two. We use equivariant vector fields as theta, but we do not perform data augmentation anymore. Okay, so ENN can be made as small as possible because in this case, DFE is always equal to 0, right? Because we will use equivariant vector fields. And we want to ask, will we lose the gain in green by this like data augmentation part of the sample complexity? So the answer is no, we still have it because it's automatically augmented by these equivariant vector fields without doing any manual data augmentation. So this is explained in the following result. So consider the ISM problem. So ISM, if you remember in the early slides, ISM are equivalent to DSM up to some constant that is independent of the score S. So consider ISM problem where rho can be non-G invariant. Then for any G equivariant vector fields S, we have these two objective functionals are equal. So this to explain this equation, so basically you use a G equivariant score matching to match the score of a generic probability measure. And so the value is the same as if you use these equivariant vector fields to do score matching with its symmetrized part, right? So this means the optimization of these non-augmented samples with this equivariant vector field is equivalent to the score matching using the same equivariant vector field with its symmetrized part, right? Without doing data augmentation manually, right? So this means, okay, you actually you only do score matching with non-augmented samples. But once you use equivariant vector fields or equivariant score approximation is equivalent to the optimization objective as if you do score matching with its augmented version. So you do not do the augmentation in advance, but once you apply the equivariant score, you automatically get the result of the score matching with its augmented version. Does it make sense? Okay. Okay, so here are some simple numerical simulations. Again, we learn a mixture of 4 Gaussians. Okay, so here is the ground truth. And the second figure is when you use equivariant score matching with data augmentation. And the middle one is you use equivariance without without data augmentation. So no manual data augmentation is in the middle. And the fourth one is when you use a vanilla score matching. So you typically you can put in like a ReLU neural network. So without any encoded symmetry. And the right one is the standard diffusion model. So without any symmetry into the model or data augmentation. So you do not do anything. So if you compare the result with the ground truth, so these two are the best, right? If you have a equivariant score approximations. Okay, so quantitatively, you have the following one distance between the generated distribution and the target distributions. So the top 2 curves plot a case where you use non-equivariant score matching neural network with or without data augmentation. And bottom 2 are the case where you use equivariant score approximation with or without data augmentation. So these two have a smaller error because they use equivariant score matching objectives. So this convey the point that model equivariance is more important than doing data augmentations.
So in the real world,
Yeah.
you really don't have finite groups or anything that can be used.
Right.
Think of, you have images, you have distortion, you have the rubber sheet, you have all possible distortions.
Right.
And so if you wanted to augment, you would not just augment by rotation.
Yes.
So you want to have a family of distortions
Mhm.
which generate enough distortions to have a good augmented data set.
Yes. In this sense, the symmetry may not be perfect, right? Maybe.
Right. I mean, in other words, the symmetry group is a group of changes of variables.
Yes. Right.
And so you need to be able to define what you mean by allowed changes of variables for a given data set.
Yes.
And that defines for you. So there's like a game thing. You have to decide which change of variable is bad.
Right.
It throws you out of the data, and
Right.
which one keeps you more or less in the same distribution.
Mhm.
Once you have this collection, you can augment.
Yes, exactly. Yes. Mhm.
So you don't need, I mean, the problem with the finite groups,
Mhm.
is they don't fit a situation where everything is flexible.
Right. Yeah, it's limited. So there's more flexibility in like, for example, filter design.
Yeah.
In the neural networks than doing like pre-specified data augmentations. So this may allow some flexibility in terms of the distortions of the group actions.
Because it is also the thing that, Malai is doing in the scattering.
Yes,
thing,
right.
which is designed to take into account the fact that you can have distortion.
Yeah.
And diffeomorphic changes of variables and stuff.
Right, exactly. Yes. Yes. Okay, so we finished the part with the structure in terms of group symmetry. And the second part of the talk, I want to talk about the other structures. So, for example, heavy tails or low-dimensional structures, something like fractals. And the point is, I want to come up with something that can be agnostic to these structures, but remain robust. Okay. So this is a class of divergence where I want to focus on. So the Lipschitz regularized alpha divergences. So before talking about that, let's review what alpha divergences is. So alpha divergences is defined as in this like probability density ratio form where you have f alpha taking in these polynomial-like functions. And in its variational form, we can rewrite this alpha divergence between P and Q as the supremum over the function class between these two embeddings. So this time we have an asymmetric divergence, unlike the Wasserstein 1 or MMD, right? Here, F alpha star is the Lorentz transform or convex conjugate of F alpha. Now the function space is very broad, is bounded measurable functions on the whole domain RD. Okay, so idea is to put Lipschitz regularization into this variational form of this. So we call it Lipschitz regularized alpha divergence, where we have replaced these broad bounded measurable functions by Lipschitz functions on the test function space. So this regularization is imposed in this sense on the function space. Okay. So you can view P as the generated or source distribution and Q as the target distribution. So it has been shown that this Lipschitz regular alpha divergences has an equivalent primal formulation. So it's basically the infimal convolution between alpha divergence and this Wasserstein 1 metric. So L is the.
Can I ask you, can you say exactly what the formula for S star, F star alpha of gamma?
Okay,
You
F,
have Lipschitz function gamma, and then you do this. Right?
right. So F alpha is defined in this form. So this is F alpha function.
Okay, F alpha is a function that you had. That's
Yes.
F alpha star.
F alpha star is the Lorentz transform. Yeah, F alpha star is the Lorentz transform of F alpha. So it's guaranteed to be convex function, no matter what F alpha is. But typically in alpha F divergence, this F alpha should be convex. So you can understand this, both F alpha and F alpha star are convex. And in the limited case, when alpha goes to 1, this recovers the KL divergence. So corresponds to the Fock-Planck. Okay. So it has an equivalent primal formulation, which is an infimal convolution between alpha divergence and the Wasserstein 1 distance. So it's upper bounded by either alpha divergence and the Wasserstein 1 distance between P and Q. Because if plug in P, you have the alpha. If you plug in Q, you have D1. So this is infinite. Okay, so we want to show that this less than or equal to can be strict less than. Okay, so here is one example. So suppose P and Q be distributions on the real line such that Px has some tails but has finite first moment, and Qx has some tails also, but they are not absolutely continuous with each other because we single out the domain between 1 and 2 for Qx. And the tail of Qx is very heavy such that it does not have finite first moment. So the alpha divergence between P and Q is infinite because P is not absolutely continuous with Q. And the Wasserstein 1 distance between them is also infinite because Q does not have a finite first moment. But it turns out this Lipschitz regularized alpha divergence is always finite between P and Q. So let's come back to this picture where you want to learn the target data distribution and you want to generate some distributions. Although on the one hand, this parameterization of the model to generate the distribution is very important. So on the other hand, this divergence to measure these two probability measures should be also important as well, right? So in this sense, it's also very important to find appropriate divergence that is suitable for a very broad class of distributions. Okay, so here are some intuitive simulations from us. So where you learn a student teeth distribution without finite first moment. So the left pictures are the generative models based on simply alpha divergence with no Lipschitz regularizations. So these red curves are the ground truths of plot of the radius complementary cumulative density functions. And the right-hand side, so these two are the one with Lipschitz regularizations. So you can see they generate better particles and also the tails is better captured. And on the other hand, if you look at other generative models such as normalizing flows, which is basically on KL divergence without Lipschitz regularization, so it's not that good. And also here is an OT flow, which is based on KL divergence with Wasserstein 2 regularization. Because I just mentioned the Lipschitz regularization in the primal form has the equivalent formulation as if you do W1 regularization. Right? So here is if you replace W1 by W2, it's not as good as well. And here is the famous diffusion models, the score-based generative models. So this looks fine in this example for the diffusion model. But if you implement in the real world data, which has even heavier tails, so it's a keystroke data, where the left two are the generative models with Lipschitz regularized divergence. And the third one is the one with W2 regularization. And the right one is the diffusion model. So now you can distinguish this is inferior to the models compared to the left two. Okay, so some explanation for this. So suppose P and Q are distributions on RD such that they have tower-like densities like that. This is a pretty strong condition, but first we just want to investigate how the tail interacts with the divergence. So we provide the sufficient and necessary conditions to suppose alpha greater than 1 and PQ are distributions with tail index as beta 1 and beta 2, then the divergence is always finite if and only if one of the following two conditions hold. So this has a relation reflects interplay between beta 1, beta 2, and dimension and alpha. So in particular, this the second case where you have the only requirement is beta 1 should be greater than d plus 1. So is that when you have finite first moment for P, right? So this has an implication that if you want to learn some heavy tail distribution, you can possibly start with some light tail distribution such as Gaussian. And even if you have a distribution with a very heavy tail without any without finite first moment even. So in this sense, you have no knowledge about the tail for the target distribution. Okay. So this is a pretty strong assumption because in the previous slides, we make an isotropic assumption on the density. Actually, you can allow the tails to be different in different directions of the domain. And even more, we can assume the domain is some star dimensional smooth embedded submanifolds of RD with Lipschitz embedding because everything should be done in a Lipschitz way. Okay. Then we found out actually there is more than this heavy tail assumption. So indeed, we found that P and Q be arbitrary Pauli measures on RD, and we only assume that P has a finite first moment. But we have no assumption Q other than requiring Q to be a Pauli measure. Then we show that suppose alpha greater than or equal to 1, so when alpha equals 1 is a Lipschitz regularized KL divergence. Then we show this divergence between P and Q is always finite whenever P has a finite first moment. So this includes case when Q have heavy tails or is supported on low dimensional manifolds or supported on fractals, something like that. So because we make no assumptions on Q. Okay, so in GANs, we have the mathematical formulation of GANs is to find the best generator. Right? We want to optimize over the generator class such that this divergence between the generator distribution and target distribution Q is minimized. Okay, so we know GAN is really a mini-max problem, so it can be formulated in this way where gamma is taken to be the class of L Lipschitz functions. In practice, gamma is also parameterized by neural nets. For example, you impose spectral normalizations on some technique like that to ensure the Lipschitzinity of the discriminator functions. Okay, then if we want to optimize this generator the parameter of the generator neural nets, we typically want to do some gradient-based method, where if you want to take the gradient with respect to the neural net parameters of the generator, it can be written in this form. where this term is the first variation of the divergence with respect to the first input. And in this sense, in order to achieve a robust generative modeling, we need a robust and well-defined variational derivative that also works with finite samples, right? Okay, so we have shown the results for the finiteness of the divergence in some condition with some conditions. So why is this important? Because with this assumption, we can prove the first variation formula of this divergence. So again, we only make assumption that P has a finite first moment. And then we perturb this P by some epsilon rho, and we prove that it has a well-defined variational formulation. It can be written as, the first variation can be written as the gamma star, whereas gamma star is the maximizer of the variational form. So in the definition of the Lipschitz regularized alpha divergence, right? In this sense, it has a well-defined variational derivative as long as P has a finite first moment. Okay, so given this result, we can even formulate the gradient flows of this, right? So here we have something like Fock-Planck, but we have no longer tail, but some Lipschitz regularized version of that. And you can write it as some integrate between initial time and target time from 0 to t. You can have a decay of this divergence between target distribution, terminal distribution with the target distributions. So such that the initial value between P0 and Q should be finite in order to successfully initiate or start the gradient flows, right? Because the decay formulation can be written in this way. So to summarize, the finiteness of this divergence between P and Q is crucial to start the gradient flow. And in order to further propagate, we need a well-defined variational derivative divergence. Okay, so it's justified for various machine learning algorithms that optimize this divergence without any assumptions on the target distribution Q. So more examples. Where we learn a 10D anisotropic heavy-tail distribution that is embedded in 110 dimensions. Okay, so the first column is the arrow for capturing the heavy tails. And the second arrow is to measure how close is the generative distribution with respect to the low-dimensional plane. So these two methods, based on the Lipschitz regularized alpha divergence, has the smallest arrow in terms of learning the heavy tails. Also, SGN is also fine in this case. And if you take further consideration into the distance to the manifold, then these two still have a reasonable error, but the SGN is not that good. So in this sense, methods based on Lipschitz regularized alpha divergences can both capture heavy tails and be close to the unknown low-dimensional manifolds. Okay, so maybe it's a final example for the learning of Lorentz attractor. So it's based indeed Lorentz 63 system. It's a chaotic system, and we want to learn the attractors. Okay, so this is when we use 5,000 training samples and measured by some MSE error. So the first row is when we have Lipschitz regularized alpha gain as a loss function. And you can in visualization, you can see it's closer to the attractor. So it's basically lies on the fractals. And if you remove the Lipschitz regularization, then it goes far away. So it's no longer close to the trajectories over here. And loss is also small if you impose Lipschitz regularization. Also, another generative models based on this Lipschitz regularized alpha divergences is gradient flow-based method. Also, in the first row is with Lipschitz regularization, you are closer to the attractor. And if we remove the Lipschitz regularization, it almost blows up. Also, the error is significantly smaller than the one without Lipschitz. Also, okay, here is more results with the same data. So you have OT flow, which is Wasserstein 1, or sorry, it's Wasserstein 2 proximal localization. So it's not as good as Wasserstein 1 or Lipschitz case. And the bottom one is the continuous normalizing flow, is basically the objective functional is the KL divergence. So they are not as good as the one with Lipschitz regularized alpha divergences. Okay, so this is the result for SGM. It's still inferior. Okay, the last part we want to talk about the finite sample estimations of this type empirical estimations of this Lipschitz regularized alpha divergence. So we provide the bound. So it's not the sharp because we require the tail index should be proportional to the dimension. So it's not really that heavy. And we provide the sample complexity bound for these empirical estimations of the divergence. So this is not sharp, but nonetheless is the first result for the estimation of the divergence on unbounded domains. Although this is not sharp, but it does have one implementations. So if we come back to the empirical estimations of divergence with group symmetry, so we at the very beginning of the talk, now we can extend it to the unbounded domain. Now we make assumption that distribution P is subwave, which means its decays slightly slower than the exponential class, right? Because theta can be greater than 1. Okay, then we provide the result for the empirical estimations. So it can also be extended to infinite group, but I just placed the one with finite group result here. So suppose P and Q are both G invariant and both subwave, and suppose the quotient space is connected and has an effective dimension greater than or equal to 3, then we have the following bound. So again, you see the gain of the group size over here. Now it's unbounded domain. But C1, C2 are dependent on the D's moment of P and Q. Similarly, so this is first results on unbounded domain with symmetry. So similarly, we can provide the Wasserstein 1 estimation bound for the divergence with symmetry. So the conditions are the same, and also C1, C2 both depend on the D's moment of the P and Q. So although these C1, C2 are not optimal, because in the optimal estimation of Wasserstein 1 distance, this dependence on the moment should be way smaller than D's moment, should be like something like D over D minus 1's moment. But the rate matches with the optimal rate. And we also see the gain of the group symmetry, like by kind of data augmentation appeared here. Okay, some future work. So we can consider equivariant models with almost symmetry, more or less similar to what Rafi mentioned. The symmetry may be not perfect. It's not exactly characterized by some group elements. And also we want to investigate if equivariant model more robust to noise compared to the vanilla one. And what is the efficient parameterization and approximation power of deep equivariant neural nets. And we can further compare equivariant models with data augmentation from gradient flow or training perspective of the neural nets. And because I said the bound for the empirical estimation is for this regularized alpha divergence is not sharp, then certainly we are working on the sharp minimax bounds on this. And also in the continuous version, can we provide well-Posner theory like uniqueness and the convergence result for the gradient flow of this Lipschitz regularized divergence? Maybe we need to post different sublog length or other functional inequalities. Okay, here's a reference. Thank you very much.
There's one slide saying the alpha Lipschitz divergence, there's a condition between beta 1 and beta 2. Right?
Yes,
You have two
yeah.
conditions. Can you explain like what's the intuition between of these two conditions?
Okay, so
Right. About the beta 1, the other two tails.
okay, so actually the first condition is very intuitive because if you forget about Lipschitz, you only consider like alpha divergence because alpha divergence can be written as some F divergence in its primal form. So maybe I should come back to the formulation of alpha divergence first. It's over here, right? This alpha divergence. Okay, so suppose now P and Q has like power like density, and P is absolutely continuous with respect to Q, and you plug in. So P is some x to the negative beta 1, and Q is x to some negative beta 2. Then this divergence is finite if and only if beta 1, beta 2, and alpha D satisfy those assumptions. And for the second part, second condition where you only require beta 1 greater than D plus 1,
Right.
this part is due to the Lipschitz.
Okay.
Yeah, this is something more than the alpha divergence.
Yeah.
Yeah.
Great.
Mhm.
No question? Let's thank our speaker again.